Welcome to part 2 of this QUPES how-to video, where we illustrate how to optimize a reflector array that consists of square patches. For this video, we continue from the previous how-to video, where we showed how to set up and analyze a periodic unit cell that will be used for the reflector array design. If you're not familiar with how to set up a periodic unit cell or a PUC, check the part 1 video. We start with the TICRA tool project, where we have created all the objects needed for the definition of the reflector array configuration. This includes the coordinate system objects, the rim and surface of the reflector array, the feet, and the reflector array object itself. In addition, a periodic MOM and a far-field cut object has been created, and they're used to carry out the far-field analysis of the reflector array. The reflector array object is defined using an object of the class Quasi-Periodic Surface, wherein a reference is made to a periodic unit cell that defines the geometry of the square patch. In the PUC tab, we can see how the unit cell looks. The reflector array is defined such that it now consists of identical elements of the size defined in the reference PUC. In the command tab, a getCurrents command is defined using a function which will be used later in the video. In this command, the source is the feed and the target is the periodic MOM object. After the currents have been calculated, these currents are used to determine the far-field pattern using the getField command. We now execute the command and let QUPES do the work. On my laptop, the analysis takes 1 minute and 43 seconds. And after it's complete, we switch to the Results tab to look at the pattern. It is seen that the far field resembles the feed reflection from a metallic plate, and this is exactly the expected behavior when the reflector array consists of identical array elements. Now we proceed by defining the steps to carry out the optimization of our reflector array. First, we need to calculate a scattering matrix database to speed up our analysis. To this end, we go to the PUC tab and select our periodic unit cell. We click on Periodic Unit Cell Commands and select the Get Periodic Unit Cell Scattering Matrix Database command. The target periodic unit cell is the rectangular patch object. We specify a file name for the database, and then we specify the parameter that we would like to vary, which is the side length of the square patch LX. We'd like to calculate the scattering matrix database for LX ranging from 0.5 to 3.8 mm for 50 sampling points. 50 sampling points are usually sufficient to ensure an accurate analysis using the database. For the sampling of the incidence angles, we use the default values. Next, we proceed to define the optimization. We go to the Optimization tab and create a new optimization manager. First, we define the optimization variables, which are the patch sizes in the reflector array. We click on New Variable, Bulk Optimization Variable, and select the target scatterer to be our reflector array object. We want to optimize the side length, LX, within the range from 0.5 to 3.8 mm. It's important to set these bounds, otherwise the optimizer will try to go beyond, and we haven't computed the scattering matrix outside this range. We activate the variables in the optimization by adding them to the box at the right. Secondly, we define the optimization goal. We want to have a pencil beam design, so we click on New Goal, Goal Specific Direction. As source, we select the feed and the PMOM object. The radiation pattern of these sources will be used to evaluate the object function during the optimization. This means that as we change the patch size in the reflector array, the PMOM currents will change accordingly. As coordinate system, we select peak coord, which is the direction where we want our pencil beam. For grid type, we use theta phi. Goal specification, coordinate 1 and 2 are the theta and phi direction, respectively, and these are kept to 0. We choose linear X polarization, and we want a minimum of 48 dBi directivity. We activate the goal in the optimization by adding it to the box to the right. Thirdly, we define the optimization settings. We'll use the min-max algorithm in TICRA Tools. We create a new optimization settings, and for this optimization, we consider only 30 iterations to speed things up a bit. And finally, we need to define the function for evaluation of the optimization goal at each iteration. This is basically the analysis that needs to be done at each optimization iteration. We've already defined the getCurrent function, and this can be used for the optimization here. To add an optimization command in the list of commands, we press Add getOptimum command, and a command is automatically generated in the Command tab. We now rearrange the order of the commands such that they're carried out in the correct sequential order. First, generation of the database, next, optimization, and third, the analysis of the optimized Reflectarray. Before executing the commands, we need to modify one attribute in the periodic mom object. In this object, we need to change the attribute analysis method to read database, meaning that we'll use the database when doing the analysis and thereby significantly reducing the computational time. We specify the name of the database and are now ready to execute the commands and let QUPES do its job. The Reflectarray has more than 48,000 elements. The entire optimization takes about 2 minutes on my laptop. But once the optimization is complete, we proceed to the Results tab to look at the results. We see that we now have a significantly different pattern compared to before. The optimized Reflectarray provides a pencil beam with a peak gain of 48.8 dBi. To have a look at the Reflectarray layout, we double-click on Optimization Variables and select Load Final Values, accept the warning, and switch over to the Antenna tab. Here we can see the variation of the array elements over the surface of the Reflectarray. And this variation is needed to compensate for the phase delay from the feed, such that we can achieve a pencil beam design. One can export the geometry of the Reflectarray to Gerber or other CAD formats such as STEP using some of the export commands in TICRA Tools. Thank you for watching this QUPES how-to video. I hope you found it useful.